So exercise number 10, this is the last part in our curve sketching, which is the second rational function. So I have already captured this y equals to x plus 1 divided by x minus 1 squared from our lecture slide for exercise number 10. I'm just going to jump straight into our first part, which is looking at the vertical and horizontal asymptote. So x minus 1 square, let it equal to 0, then you will get that x equal to 1 may be the potential candidate for the vertical asymptote. So writing it like this, limit of x approaches towards 1 from the left of y is equal to, yes, again for this one you just simply need to use your calculator, and then you get a very big positive value. And then if you try to substitute x approaches 1 from the right for y, you will get also a positive big value. This is due to the fact that the x is operated first and then it's squared. So when it's squared, everything will become positive over here. But the most important thing is we already obtained the conclusion for the vertical asymptote, which is x equals to 1. So if we put a tracker up here to track our progress, we already have one vertical asymptote and the value is 1. For the left of it, it's going to be positive infinity. From the right side, it's going to be positive infinity as well. So it goes to show that the curve might move something like this, and if it's from the right, it goes towards up like this too. Okay, so next is horizontal asymptote. So we need to evaluate the limit as x approaches towards infinity for y. We are using the highest power of x in denominator, which is x square. Definitely this one, if you expand it, you get an x square and minus 2x plus 1, so it's going to be x square. And since at the top over here you only have x to the power of 1, then it's very easy to see that it's going to be 1 over x plus 1 over x square, and you get a 0 over here after you substitute with infinity. So this one is the conclusion for our horizontal asymptote, which is y equals to 0. Now we have additional information here, which is y equals to 0. So let's put it maybe here. Okay, so moving along, we have number 2. Differentiate y to obtain negative x minus 3 divided by x minus 1 to the power of 3, and then let it equal to 0. This time around we have a candidate for a turning point or a stationary point, which is when x is equal to negative 3. So the corresponding y value will be I think since we have never declared fx over here, so let's just don't use it, since when x is equal to negative 3, then simply substitute it back here, then you get your value of y, which is a negative 0.125. So stationary point is negative 3, negative 0.125. Okay, so for the rational function case, we don't need to actually test whether this one is a maximum or a minimum point, because as we sketch the behavior of the curve, the maximum or minimum property will present itself to us. So we just have to note that there exists a stationary point somewhere in the -3 and -0.125, and if we take a look here, the stationary point might be somewhere to the left and to the below of the axis. Let's just use it here, assuming that if we have a axis or y-axis over here and x-axis over here, enclosing on this horizontal asymptote. So there's a stationary point down here, down and left. Okay, so let's go to the number 3, which is finding the intercepts. So when your x is equal to 0, then you get 0 plus 1, 0 minus 1, and then square, it is simply a 1. So you get 0 and 1. And when your y is equal to 0, then x plus 1 equals to 0. So you just simply have a -1 and 0. So those are the intercepts. Okay, so for number 4, the domain and range. Again, we are going to leave this one first before we can actually see it, but let's wait for the graphical to finish. I just noticed just now that in the previous video that we haven't answered for the domain and range, even after we have obtained the graphical information, but it's okay. In this video we will definitely do not forget to answer this number 4 and number 5, which is evaluating the behavior as x approaches towards -infinity and also +infinity. Alright, so when x approaches towards -infinity, we will get a value something like a -0 point, etc, etc. So it goes to show that the -0 point something is corresponding towards the horizontal asymptote. It's below or before the horizontal asymptote, so it's going to be 0 minus. Hopefully you are used to this notation. And yes, if we take a look at this tracker, so as the curve goes to the left, it is below the horizontal asymptote, and if we evaluate limit as x approaches towards the right, you will have a 0 point something, a positive. So it's a value a little bit above this horizontal asymptote, so we are using 0 plus here. So as the curve goes to the right, it should be here. So note that if we take a look at this tracker, this is a stationary point. Maybe you'd like to use a deep circle here to signify its presence. So the curve moves something like this and then produces like I said, the relative minimum or maximum will present itself to you. So it goes something like this, and then for this side, since there is no stationary point, so it's just the curve, simple curve movement according towards the asymptote. Okay, so now that we have this tracker full, we already can see the graphical information for this curve. Then you can say that for the domain, the x can be any value from -infinity towards +infinity except for this vertical asymptote. So you can write it x is not equal to a 1 like this, or maybe some people love to write it in interval notation. So for interval notation, it will be -infinity towards 1 exclusive union 1 exclusive towards +infinity. Never mind, I will write it in different color after this. So for the y, again, you can see from this curve that the lowest point of y is this one, which is our minimum point. So it's going to be from -0.125, it can goes up. Some people may say that it will not touch the horizontal asymptote, but as you can see over here, this line is actually from -0.125 goes up to 0 and goes up towards +infinity. So you can write y is from negative 0.125 inclusive y, and okay, so I think I write it wrongly. I just simply need to write y is greater or equal to negative 0.25. Okay, so for the interval notation, let's use the red color. You can say that this one is from negative infinity towards a 1, and then 1 towards positive infinity, and this one is from negative 0.125 inclusive towards positive infinity. Okay, so let's just redraw our curve properly. We can simply draw the asymptote first to guide our lines. That is the horizontal asymptote, and we have vertical asymptote. So you are going to see that the curve goes down, and then there's a stationary or a turning point, and then it approaches there. And for the right side, it's going to look like this. Okay, so this in itself is our x-axis, and this one is a 1, so the y-axis should be here, but we need to take a look whether it should intercept on the positive side or is it intercept on negative side. Just take a look at our intercept. 0 and 1 means when the x is 0, then the y value is equal to 1, so it goes to show that it intercept at here. So this is your 1, this is another intercept which is a negative 1, and stationary point, maybe labeling it here will be good enough, negative 0.25. Well, it's not really following the scale, but since it's a sketch, it's just a sketch, then it should be good enough. Alright, so that is our vertical asymptote 1. So as you can see, we can actually tackle a lot of different type of rational function by following this 1, 2, 3, 4, 5 important criteria or points. Just make sure that you know how to evaluate a limit and when to use your calculator to actually help you to discern this, especially on the behavior side. Okay, to get this value that corresponds to our horizontal asymptote, whether it be below or above the horizontal asymptote. So hopefully that helps you in your rational function, and that marks the end of our subtopic 2.3, the curve sketching. So stay tuned for more. We will have the last subtopic, which is 2.4, the rate of change, in the later video. So stay tuned until next time.